Welcome to the second part of the tutorial on machining. We have discussed certain operations, lathe cutting operations, milling operations in the first part. In this part, I will cover the single point cutting tool, that is the orthogonal cutting, the angles of the tool, the chip thickness ratio, etc. that would be covered. Then we will try to see the numerical problems on the tool life equations. This is a tutorial session on machining. I am Dr. Amandeep Singh Oberoi. To recall the concepts on orthogonal machining, that is two-dimensional machining analysis, this is what that we have discussed in the theory part, that there is a chip that is being removed from the workpiece. This green color is my workpiece, and this is chip, yellow color, and red color is my tool. This is alpha, that is my rake angle. It is given, all the notations are given here. Beta is the frictional angle that is given here. Shear angle is phi. This is shear angle. The shear plane, this is shear plane. The angle made by shear plane to the base is phi. And T naught and TC are the uncut chip thickness and cut chip thickness respectively. Then there are cutting forces such as PS is cutting force, or we also call it as tangential force. Then PT is thrust force, we have shear force, normal shear force, frictional force F, normal frictional force, cutting velocity, chip velocity, shear velocity, and length of shear plane. This is along the shear plane, what is the length? This all is discussed already in the previous lectures. You have seen the NRS, ORS, ASA, different kind of the cutting morphologies, and NRS is more explained there. Let me now come to the relations that we will use to solve the problem statements. Shear angle may be obtained either from the photomicrographs or assume volume continuity, that is no chip density change. If it is considered that chip density remains same, that means the volume also remains the same. Volume is what? Thickness into width into the length of the uncut chip, that is equal to the thickness into width into length of the cut chip, where W naught and WC are experimental evidence only, and cutting ratio R T naught by TC is equal to LC by L naught is equal to also sometimes noted as T1 and T2. It is chip thickness before cutting, that is uncut chip thickness, and chip thickness after cutting, that is cut chip thickness. That notation is given here. The higher the cutting ratio means less chip compression. This results in better surface finish and reduced cutting forces. This is LC, that is the length of the chip, and this is L naught, that is length of the uncut chip. Here you can also see it is again given the rake angle, the shear angle, we have the length of shear plane here. This is my LS, length of the shear plane. Here sin phi is equal to T naught by AB. If this length of shear naught is AB, sin phi is T naught by AB, that is cos phi minus alpha is equal to TC by AB. So chip thickness ratio T naught by TC could also be put as sin phi by cos phi minus alpha. That is, we take the ratio of here. So how has it come? If I put this as equation 1 and this is equation 2, so equating AB in 1 and 2, we get this equation. And this is our relation that we will use to find the shear angle, to find the rake angle, to find sometimes the cut chip thickness that will be obtained. Also, the ratio, that is T naught by TC, that is the cutting ratio, is equal to LS into sin phi by LS into cos of phi minus alpha. Right, I have introduced the term LS here. This gives me tan of the phi is equal to R cos alpha by 1 minus R sin alpha. So these will be used in the calculation and also for minimum shear strain condition. It comes when 2 phi minus alpha is equal to 90 degree. We get 2 phi minus alpha here, that becomes 90 degree. So that becomes when the shear is minimum. So that comes when the shear is minimum. And if suppose we wish to calculate the velocity Mn, so I will put here in this direction we have the chip velocity Vc, then we have shear velocity in this direction Vs, then we have cutting velocity in this direction, that is V. This is cutting, this is chip, and this is shear. These are velocities. So if I put here the mass continuity equation, that is before cutting, that is cutting speed into the thickness before cutting, uncut chip thickness is equal to the velocity of the chip into the chip thickness. This gives me V C is equal to V into R. This R is my cutting ratio. This also gives me a relation, that is shear velocity is equal to cutting velocity times cos alpha by cos phi minus alpha. So where has this come from? It has come from velocity diagram. It could put something like this. For example, this is my velocity vector V, and this is my vector Vc, and here comes the shear vector, this direction Vs, and this is angle phi. Here if I draw a perpendicular line here, if this is suppose 90 degree, this becomes 90 minus phi, and this becomes phi minus alpha. So this is known as velocity diagram. So let me come to problem statements so that we understand this and try to see how do we get the solutions, how do we get the answers to the questions that are asked. First problem is find out the shear angle of a single point cutting tool which has rake angle of 12 degrees, depth of cut as 0.81 millimeter and chip thickness as 1.8 millimeter. We have been given alpha is equal to 12 degrees. We have also been given the depth of cut D is equal to 0.81 millimeters, and we have been given the chip thickness as TC is equal to 1.8 millimeter. So here uncut chip thickness is not given, depth of cut is given. If I put deep my tool, the distance that it goes in, then that distance that is indented in here, that distance is equal to my uncut chip thickness. So in a way this D is equal to 0.81 millimeter. This is my T naught, that is it is uncut chip thickness. Now to calculate the shear angle, tan phi is equal to R cos alpha by 1 minus R sin alpha. So here value of R is to be calculated first. What is R? R is equal to the cutting ratio, that is T naught by TC is equal to 0.81 by 1.8 is equal to 0.45. So this value of R will be put here. and alpha value is also given. We get 0.45 into cos of 12 degrees by 1 minus 0.45 into sine of 12 degrees. This gives me the value of tan phi as 0.4861. Now phi is equal to tan inverse of 0.4861. This is equal to 26 degrees. That is the answer. A similar problem statement is given again, where they only say determine the shear plane angle for minimum possible shear strain condition when the rake angle of the single point cutting tool is 12 degrees. It is kind of the same problem, only we need to apply the minimum shear strain condition. Find the shear plane angle. Phi is to be found. We have been given alpha, that is equal to 12 degrees. Simply the minimum shear strain condition is 2 phi minus alpha is equal to 90 degree. Putting the value of alpha here, we get 2 phi minus 12 is equal to 90 degree. This gives me phi is equal to 51 degrees. Such a simple and direct problem. Next problem is similar to what we did in the first problem, that is we have orthogonal machining operation, chip thickness and uncut chip thickness are equal, that is T naught is equal to Tc is equal to 0.45 millimeters. Rake angle is 0 degree, alpha is equal to 0. We need to find phi. So it is very simple question. Here R is equal to T naught by Tc. This is equal to 1 because both of them are equal, and you can simply calculate again tan phi is equal to R cos alpha by 1 minus R sin alpha, as we did in the previous problem here. So here value of alpha is 0 degree. So even without using calculator, we can calculate this R into cos alpha. Value of R here is 1 cos 0 degree by 1 minus 1 into sin 0 degrees. So cos 0 is 1, tan phi is equal to 1, and 1 minus sin 0 is again 1, 1 by 1. So that means phi is equal to tan inverse of 1. Phi is 45 degrees, that is phi is equal to 45 degrees, or this is equal to pi by 4 radians. So I have taken very simple problems in the orthogonal cutting because this is the basics of machining course. We can go deep into calculating the rake angle, different conditions of the chip when chip is having variation depending upon the thermal properties, depending upon the depth of cut that varies. Then in the taper as well, there could be certain problem statements that could be little more deep when we have to dive into it. So these problems will only give you brief introduction. To have more details, you can maybe visit courses on metal cutting which talk about specifically orthogonal cutting. Now I will come to the simple problem statements in the tool life. Taylor's tool life equation. To recall Taylor's tool life equation, tool life is mainly affected by cutting speed, means higher the cutting speed, the smaller the tool life. Taylor gave the relation between the cutting speed and tool life, that is V T power n is equal to C, where V is cutting speed, T is tool life, C is machining constant, or it is also called a Taylor's constant, n is tool life exponent that depends upon the tool type and work material. Taylor's exponent n depends only on tool material majorly. Taylor's constant depends on tool material, workpiece material, cutting conditions, etc. The dependency of tool life on various parameters in decreasing order is given as cutting speed is having higher effect, then comes feed, then comes depth of cut, then comes nose radius. So here tool life is mainly affected by cutting speed, means higher cutting speed, smaller the tool life as it is given here. If we take log on both the sides, log of V plus N into log of T gives us log of C. This is generally calculated. This becomes a simple equation of a linear line. You see here, this is log of cutting speed, this is intercept. So this is V1, V2, V3, 3 points are given, and here we can see as an intercept n is equal to log of V2 minus log of V1, that is Y2 minus Y1 by X2 minus X1, that is log of T1 minus log of T2. So this is cutting speed, and here we have the tool life. This is log of tool life, that is T. And there are certain Taylor exponent numbers which are given for high speed seal because it is dependent majorly on the tool type, tool material. It varies from 0.08 to 0.2 for high speed seal, and harder you go down, the higher is the exponent value. So it is harder or highest for the ceramics, it is from 0.5 to 0.8. This is the value of N in general, that is cutting speed versus tool life that you have already seen. If this is cutting speed, this is tool life T, this suppose it given in minutes, and cutting speed if I give it in meters per minute, it is something like this, because you can see an exponent Vt per N is equal to C. So as the cutting speed is decreased, the tool life is increasing. At the higher cutting speeds, the tool life is lower. So this is our hyperbola here. So let me come to the problem statements directly. First problem says determine the value of exponent and constant of Taylor's tool life equation for a cutting speed of 60 meters per minute, and the corresponding tool life is 81 minutes. And for a cutting speed of 90 meters per minute and corresponding tool life is 36 minutes. We have been given the values of the exponent and the value of T here. At cutting speeds are also given. If I say V1, T1, and I have been given V2 and T2. What is V1? Cutting speed is 60 meters per minute. T1 is 81 minutes. V2 is 90 meters per minute. And at this cutting speed is 36 minutes. So we need to find the exponent and constant of the Taylor's tool life equation. So it is given that this is a single equation, V1 T1 per N is equal to V2 T2 per N. Let me put the values here. I can simply here say T1 by T2 per N is equal to V2 by V1. So I can take log now, or I can talk log later. I can see, okay, directly even put values here. T1 and T2 is 81 by 36 per N is equal to V2 by V1, that is 90 by 60. So now taking log, I can put N into this ratio. T1 by 36 is 2.25. Log of 2.25 is equal to log of 90 by 60, that is 1.5. This gives me the value of N as 0.5. or this is my exponent value. Now I need to find the constant value, that is in this Taylor life equation, Taylor's tool life equation. V1 T1 power N is equal to V2 T2 power N. This is equal to constant. So this constant is equal to V1 T1 power N. This is equal to 60 into 81 per 0.5. This gives me the value of C as 540. This is how we determine the Taylor's tool life equation. The speed and tool life it is given, the exponent is calculated based upon that exponent. Finally, we get the value of the constant. At any different speeds, this curve will hold good. This parabolic curve will hold good, and this curve could be drawn from these 2 points. We can even find some other points and try to draw this curve. Similarly, there is another problem statement in which again V1 and V2 are given, T1 and T2 are given. determines the Taylor's constant tool life exponent. This you can do by yourself, simply again using V1 T1 power n is equal to V2 T2 power n is equal to constant. The unknowns are n and c. This you need to find. Answers I'll give you. Answers you will get is n is equal to 0.3 and c as 512. Now let me try to see another problem statement which is other way around. We need to calculate the speed. In this problem statement, there are two cutting tools. Tool 1 is given by V t power 1.6 is equal to 3000. Tool 2, it is given V t power 0.6 is equal to 200. Determine the cutting speed at which both the tools provide same tool life. Now, this is an interesting problem. For the first tool, this is the equation. For the second tool, this is the equation. Let me say this is a point V naught and T naught. At this point, both the tools provide the same tool life. It is something like this. The hyperbolic curve that we draw, this is cutting speed, this is tool life. It is one tool here, then we have second tool here. Let me say for example, this is carbide, this is HSS. There is a point here of the cutting speed V naught where the tool life is same. This we need to find. So here V naught T naught power n is equal to constant. This we need to determine. So for both the equations which are given, let me say V naught power 1.6 is equal to 3000. This is first equation. Second equation is V naught T naught power 0.6 is equal to 200. If I take logs on both sides, now I am taking log of V naught plus 1.6 into log of T naught is equal to log of 3000. This is my equation 1. I'll call them equation A and B. This is 1. This is from A. For the second equation that is taken from B, I will put log of V naught plus 0.6 log of T naught is equal to log of 200. This is equation 2. This has been taken from B. So these becomes two kind of a linear equations with two variables. So V naught and T naught. So solving 1 and 2, I get V naught is equal to 39.4 meters per minute. This is the answer. The speed is 39.4 meter per minute at which both the tools provide the same tool life. So this was an interesting problem where we have understood also the hyperbolic curve, that is the plot between the cutting speed and tool life. For different tool material, for example, HSN and carbide I have put here, there could be or there is sometimes an intersection point where the cutting speed and tool life are same for both the different materials here. Let me now take a problem. We will try to see the intercept on the line in this hyperbolic curve, how the intercepts are plotted, and while taking log as well, how the intercept are plotted, and how do we try to see or understand the difference between the coordinates and try to find the values of the different parameters. For example, if we need to find a tool life for a critical wear length of 1.8 millimeter, during the machining, the wear length H has been plotted against the machining time. So there is a plot given here that this H land in millimeter and this is tool life T in minutes. It is plotted something like this. At the value of H2, the tool life is 60 minutes, and at the value of h 0.8, the tool life is 10 minutes. Here simply we can just calculate, because the intercept is given, we need to find the wear land of 1.8 millimeters. That is, at 1.8 what would be the value? So at the value of 1.8, this we need to find. I could say I have been given h1, h2, this is 2, this is 0.8. Similarly, I have been given T1, T2 corresponding to H1. T1 is 60, and corresponding to H2, T2 is 10. I need to find T0 corresponding to H0. T0 has to be found at H0 is equal to 1.8 and T0 is question mark. Simply we can put using the coordinate axis here, taking this as a straight line or assuming this as a straight line here. Here these three coordinates I can equate, that is intercept, that is h1 minus h2 by t1 minus t2 is equal to h0 minus h2 by t0 minus t2. Putting the values, 2 minus 0.8 by 60 minus 10 is equal to 1.8 minus 0.8 by T0 minus 10. This gives me the value of T0 as 51.67 minutes. That is, at the wear length 1.8, the tool life is 51.67 minutes. That is the last problem statement in this tutorial, where an HSS tool is used for turning operations. The tool life is 1 hour when turning is carried at 30 meters per minute. That is, T1 is equal to 1 hour, and here V1 is equal to 30 meters per minute. And then it says tool life will be reduced to 2 minutes if cutting speed is doubled. Cutting speed is doubled, that means V2 is 2 times of V1, that is 60 meters per minute. And at this status, the T2 becomes 2 minutes only. 2 minutes. Then they say find the suitable speed in RPM for turning 300 millimeter diameter rod, so that tool life is 30 minutes. So T0 here I am putting is 30 minutes. It is under question, and we need to find V0. What is the suitable speed here? And they are asking that in RPM. Correspondingly, I will have to find N0. To calculate this, we will equate using this equation: V1 T1 power n is equal to V2 T2 power n is equal to V0 T0 power n. From this equation, we will find the value of n, that you will find as 0.203. Putting this value of n anywhere, you can find the value of V0, that will be calculated as 34.532. I am just leaving it for you so that you calculate it and try to confirm the answers here. This you will get. Now they are asking find RPM using the RPM, that is cutting speed is equal to pi d n by 1000. We can find the value of n here. You will get value of n as 36.64 rotations per minute. So with this, I am closing the tutorial on machining. In the next lecture, I will talk about the demonstration, that is the virtual lab demonstration on machining. In the next weeks, the 2 weeks which are left, we will be covering the non-conventional machining in the week 11 and sustainable manufacturing in week 12. Thank you.